Our next goal is proving the Whitney embedding theorem for the case of compact manifolds. Indeed, we will show that if we have a compact manifold of dimension m, it can be embedded in R2 times m plus 1. In order to do this, first we build an embedding from our manifold to a Euclidean space of very big dimension by using partitions of unity, and then we use a transversality result in order to reduce the dimension of the target space. This transversality result is going to be Sard theorem that we are going to introduce in this lecture. Let F be a differentiable map. We already know that the preimage of a point in the manifold N is a submanifold of N of codimension equal to the dimension of N if this point is a regular value. But there are a couple of questions that we can make that are interested in this contest. First question is, are there regular values? Because if there are not regular values, then we cannot apply this result to any y. And if there are regular values, are there many of them? That's also an interesting question, and it's going to have an impact in approximation results. The answer to these questions is positive and is given by Sard theorem. It says that if we have a CR map F between two manifolds M and N, and we assume that R is greater than the maximum of M minus N and 0, then the set of critical values of such a map has measure 0. And the set of regular values is going to be residual and thus dense in the target manifold. Let us going to explain now the components, the ingredients of this result. Let us see that it is necessary to require that M is second countable in order for the Sard theorem to hold true. Indeed, let us consider a map FA from a copy of the real line RA to R that sends every point in the line in the copy of the line R to A. Of course, the set of critical points of this map is the whole line RA, and the set of critical values of FA has just one point, which is equal to A. Now, obviously, RA is a one-dimensional manifold, yeah, and we can consider the union of all RAs where when A varies in R as a one-dimensional manifold with the narrow local charts. Of course, the issue is that this manifold is not at all second countable. But what happens now is that if we define F as a map from this one-dimensional manifold to R that sends a point X which belongs to RA to the point A, what we get is that all the points in the line are now critical values, right? The critical values of F are now all the points of the line. And so it's not true that this set of critical values has measure 0. What we have to understand here is that the Sard theorem is actually a local result. And we're going to find a neighborhood of every point in M such that the image of the critical points in such a neighborhood is actually of measure 0. But if we don't have that there is a countable base of pin sets, it could happen that we could get uncountable many of these neighborhoods whose image of their sets of critical points is of measure zero. And the uncountable union of sets of measure zero is not necessarily a set of measure zero. So we need this condition, the fact that M is second countable, in order to globalize the theorem, right? And it is much easier to work with measure zero sets if we are actually considering a situation in which the manifolds are second countable. Okay, let's point out that here in the theorem, the set that has critical values, the set that has measure zero is the set of critical values. As we already saw, if we consider a map from the line to the line, that it is the constant map, in here, the set of critical points is the whole line. So of course, it's not a set of measure zero, and the set that has measure zero is the set of critical values, okay? So that is something that we have to consider. The theorem provides a property for the set of critical values. And it sets more than just that the set of regular values has a complementary that has measure zero. It sets that it is a residual set, okay? What does this mean? It means that a set is residual by definition if it contains a countable intersection of dense open sets. And in a manifold, a residual set is dense by the Berg category theorem. So that's the reason because the set of regular values is actually dense, okay? Let us define a measure zero set. First of all, we are going to assume that it is known the concept of a measure zero set in Rn. Measure zero for Delbecq measure. And what we want now is generalizing this concept for manifolds. So for a manifold, we say that a subset C of such a manifold has measure zero if for any point x in the manifold there exists a local chart phi whose domain contains the point x and such that the image by the local chart of the intersection of the domain and C has measure zero. So essentially, what we are saying is that in the neighborhood of every point, we're using a local chart such that locally, by using the local chart, we see that the image has measure zero, okay? But it is not clear from the definition that if we consider any local chart phi, then the image of U intersection C has measure zero, because we could be using other charts a priori for the points of this intersection in order to show that locally the measure is zero. Okay, so we are going to try to show this result. If C has measure zero and phi is a local chart, then the measure of phi of U intersection C is also equal to zero. And so our definition is going to be good because we don't have to worry about the choice of local charts. Okay, so consider now a point X in M. A point X in U. What happens is that by the definition, there exists a local chart psi, that is defined actually in U prime such that X belongs to U prime and the measure of the image by psi of U prime intersection C is equal to 0, right? Okay, but what we want to see now is the following claim, is that the image by phi of U intersection U prime intersection C has actually measure 0. And why is that? This is one of the points in which we are going to use that we are working with differentiable manifolds, okay? Because we have this change of coordinates, okay, between the image by psi of the intersection of U and U prime and the image by phi of the same set. And this map is CR, if our manifold is CR. In particular, it is C1. And something that we're going to use is that the image of a measure 0 set by a C1 map still has measure 0, okay? We can use, for instance, the change of coordinates formula in order to show such a result. Okay, but okay, we know that the measure of psi as psi of U intersection U prime, sorry, it was U prime intersection C is equal to 0, okay? So that implies that the measure of C of U intersection U prime intersection C is equal to 0 because obviously it's the measure of a smaller set, so it has also measure 0. And now we can use that the image of this set over here by the diffeomorphism, which is the composition of psi, the inverse of psi and phi, has also measure 0. So in this way, we get that the measure of phi of U intersection U prime intersection C is 0. Okay? But what we are actually saying in this way is that we were considering at the beginning a point X in U, and U intersection U prime is an open neighborhood of the point X in U, of course. And what we're saying is that for every, actually, we can even work in, we could even say that the image by phi of u intersection u prime is a neighborhood of the image of x by phi. Okay, so for every point in the image, there exists a neighborhood that neighborhood would be set. Okay, such that, so it's a neighborhood, such that the measure of the intersection of such neighborhood and phi of c is equal to 0. And now using that, we can write down phi of u as a countable union of these neighborhoods, and that the countable union of measure 0 sets is actually a measure 0 set, then we deduce that the measure of phi of c, of phi of, if you want here, in order to be much more precise, okay, should be u intersection. Okay, let's make it like this. And again, by using this, by using that, we can actually write down phi of u intersection c as a countable union of the sets that of these neighborhoods, u intersection u prime. We deduce by using that the countable union of measure 0 sets has measure 0. We deduce that the measure of phi of u intersection c is equal to 0, which is the result that we wanted to show. Okay, so what we get is this remark over here. If c has measure 0 and phi is any local chart, then the image of u intersection c has also measure 0. Okay, and so we could provide an alternative definition of measure 0 set, because we could just say that a subset C of a differentiable manifold has measure 0 if for every local chart the set phi of u intersection C has measure 0. Okay, it's a little it's a little bit more simple than the previous definition, okay, in order to write down, because we don't have to consider now a condition for every point of the manifold, but the previous definition was probably easier to use in practical applications, right? So we will see an application of Sard theorem in the proof of Whitney embedding theorem. Indeed, it will be used to show that we can obtain transversality of certain projections up to small perturbations. Indeed, the proof of the simple version of the Whitney embedding theorem that we are going to see has two parts. Let's point out first that locally the theorem has no interest, because it is clear that locally a manifold can be embedded into a Euclidean space just by using local charts. At that point, we need a tool to go from local to global, and that tool is going to be partitions of unity. Once we get the embedding from our compact manifold to an Euclidean space, maybe of very big dimension, we are going to use a transversality result in order to reduce the dimension of the target space. And essentially, that transversality result is going to be just a version of Sard theorem. That's where Sard theorem enters into the proof of linear embedding theorem. Thank you for your attention.